for inviting me. Thank you for having me here. And thank you for having had so much trouble and solving problems. Thank you also very much, Professor Kucheva. And I made a little change in the program, and I discussed that tomorrow I could give a lecture which is very near in topic to the lecture which are planned for tomorrow, which are going to be given by Professor Poznera. Now, the topic which I chose for today, because of the change, is something which is rather general, and maybe it seems far away from what you are doing, but I think it only seems so. One could say that semiotics has some central topics and also concepts, such like the concept of a code. Once not very many people know what a code really is, there are a number of, let's say, alternative options for defining codes, and I'd like to show you what the concept of code can achieve when you use it. But of course, that's the general, let's say, systematic motivation for me. I also have a motivation concerning the topic, the historical topic. So I will start with a small citation of a Latin American author, and it will be one possible answer to the question why we use the sign system for numbers, which we have all over the world now, why we use that one and not another one. And the question is very simple. Imagine that you yourself are the philosopher Leibniz. Leibniz asked, who was an expert, who was asked by the King of Sweden whether one can improve our number representation system. Now, number representation, of course, that's something which I think when you first go around the world or go to other very far away countries, you are amazed that you don't understand anything but numbers you can understand. Because they use numbers, number representations all over the world in the same way nowadays. This was a long story, and I'll talk about this story, the origins of our number system. But to go back to Leibniz and the Swedish king in the early 18th century, the Swedish king asked Leibniz, what can we do with our numbers? Are they good or not as they are? Shouldn't we improve them by, let's say, change maybe the signs, the number of signs, or change the structures which we want to give the number systems, also the complex numbers which we have? Should we change the difference between complex numbers and, let's say, primitive numbers? Let me answer this question in the words of, let's say, Borges, the author, and he wrote a story, which is a short story, we can say, about Funes the Memorious. And you could give me the second slide now. These are examples of what Funes the Memorious, who was a shepherd boy, proposed as principles and also as examples for number representation. Now I'm quoting Borges. Out of the darkness, Funes went on talking to me. He told me that in 1886 he had invented an original system of numbering, and that in a few days he had gone beyond the 24,000 mark. He had not written it down, since anything he thought of once would never be lost for him. His first stimulus was, I think, that the discomfort at the fact that the famous 33 gauchos of Uruguayan history should require two figures and two words, maybe 3 and 3 or 33, in place of just one single word and a single figure. He then applied his principle to the other numbers. In place of 7,000, 7013, he would say, for example, Massimo Perez. In place of 7014, he would say the railroad. In place of 500, he would simply say 9. For each word, he had a particular figure, a kind of mark. The last in the series was very complicated. I tried to explain, I'm still quoting, I tried to explain to him that this rhapsody of incoherent expressions was precisely the opposite of the system of numbering. I told him that saying 365 meant saying 3 hundreds, 6 tens, and 5 ones. A segmentation which expressions such as the Negro Timoteo or fur blanket did not afford. Phyllis did not understand me, says Borges, or he refused to understand. So I've written some of those examples so that you can see them once more. So 33 was for him too complex. He wanted to have one single name instead of 33. The same is true of 7013. He said that Massimo Perez is much simpler than 7014. The railroad is much simpler than 7014. 9 is much simpler than 500. So this was the idea of this shepherd boy. I hope this shepherd boy idea is not too absurd for you, because we have to put our mind into that mind in order to understand the problem. And what Borges now says, and I just quoted him, is that for 365, which is a good example because it happens to be the number of days in a year, we say 300, 6 tens, 5 ones, so 3, 6, 5, and that's what we write here, and this somehow determines the structure of this number representation, and by that also the structure of the number system, because the number systems which we all use in the world now depend on this structure, the fact that we can use the structure to give representations that are virtually infinite. One would have to go far back in the history of mankind to find a culture which proceeded like that Uruguayan shepherd boy and expressed all its numbers with a collection of unrelated expressions. Nevertheless, it can be argued that no system of number representation can quite do without elementary science of this type. So what you see here is Massimo Perez or the railroad or 9. These are simple, more or less simple expressions. And the question is whether not all systems for the representation of numbers need such expressions. What Borges says is yes, we need such simple expressions, and that's what I'm following up now by arguing in the following way. Our own number words under 10 and our Indo-Arabic numerals do not show either how the numbers designated by them are related to each other. So nothing in the form of words like 8 show that 8 is double 4 or 4 times 2. This is not to be seen from these primitive terms 2, 3, 4, and 8 or 9. And our system, like the other systems that have been proposed, they have all those primitive and simple expressions, but they don't have them only. They also have principles for the construction of complex numbers or complex number representations by means of these simple numbers. So the main point, of course, is that by establishing a fixed series of words or figures which corresponds to the rising sequence of numbers designated by them, that's how we learn to count. So counting and the system for number representations are immediately related to each other. And one can say that the part of the procedure which most burdens our memory ends at 12 in our system. As the numeral word 13 already can be analyzed in the two parts, third and teen. which remind us of words. We meet words which we met in the preceding series 3 and 10. With the figures, this occurs even earlier at 10. So when we write 10, this is the first time that we have two figures which are concatenated, namely 1 plus 0. And by composing numeral expressions out of other numeral expressions, we are spared continually having to learn new expressions, and our memory is not needlessly burdened because we keep the lexicon of our science system small. Who has at his disposal the memory capacity of Venus, this shepherd boy? And if so, nobody has that memory system. Who could use it with ease? Nobody. Simplicity in the lexicon is, however, not available without extra cost. So whoever understands the meaning of words like 13, 14, and so on, and because he knows the meaning of the word of the constituents, namely 3 and 4, or third and 4 and teen, does so by following certain rules, and these rules must be learned like elementary science, which makes them also burden our memory. To be more precise, we are dealing here with rules of very different types. One is a syntactic rule, which determines the pattern according to which the elementary signs are combined into complex signs, and another type of rule, a semantic rule, which determines how the value of this complex sign is derived from the value of its constituents. In the present case, we need the syntactic rule that numeral words between 3 and 9 may be combined with 10 into a new word by having T attached to the end, not the other way around, otherwise it would be an incorrect form like T4, not 14. And we need the semantic rule that the value of a word composed in this way is derivable from the value of its parts by addition and not by multiplication, since 4 plus 10 is 14, but if we interpret 4 plus 10 by using multiplication, then 4 times 10 equals 14, and that's not what we need. So we have 3 types of rules, but 2 types which I'm talking about now. One is a syntactic rule, the other one is a semantic or lexical rule. These examples show that a system of number representations, like every science system, consists of a lexicon, a set of syntactic rules, and a set of semantic rules. Furthermore, a comparison of the numeral expressions of fewness with the English numeral words and Indo-Arabic figures shows that one and the same subject matter, in this case, the natural numbers 1, 2, 3, can be represented by completely different sign systems. So we have a system of numbers, but we have many different systems which are possible alternatives for representing the system of numbers. Could be the Arab system, but we have other systems which we talk about them and compare them now. It's the general task of sign theories, and sign theory and semiotics is for me the same, to explore possible structures and functions of sign systems. That's what I call theoretical semiotics. To describe and compare actual sign systems, that's what I call descriptive semiotics, and to recommend particular sign systems for particular purposes, or if necessary, to devise new sign systems. That's what I call applied semiotics. Our desire to fulfill our needs with the least possible effort plays an important role in the development of these sign systems. But how does this mental effort, which is necessary for the learning of a new, compare with the effort necessary for learning a new elementary sign? Suppose we have, or we live in an Oceanian culture, where there was only a need for the expression of numbers under 20. In this case, not a system like that of fewness with the lexicon of 19 elementary signs, and without additional syntactic and semantic rules, be preferable to the one which we have, with 12 elementary signs, 1, 2, 3, 4, and so on, until 12, and then the new rule, namely 13, 14, 15, and so on, until 19. What is easier for us as a memory effort? That's the question here. And does it require less effort or more effort to learn 2 grammatical rules and 7 elementary signs, which we do in our system? These are questions concerning economy of science. Naturally, they cannot be answered independently of solutions which the culture in question has found for related problems in other areas. For example, the learning of a science system can be considerably facilitated by the fact that its elementary signs are elementary and are already used by the learners in other contexts of their culture, and their meanings are characterized by relationships that are analogous to those that hold in the other contexts. An example is the Egyptian science system for number representation. The Egyptians who were already using numeral systems more than 5,000 years ago were able to represent nearly 1 million numbers with only 6 hieroglyphs. Not without reason did the Egyptians consider their country as gift of the river Nile. The river Nile, which in an annually recurring pattern burst its banks and flooded the desert to fertile mud. These circumstances determine the economy, tillage and husbandry, the trade, farming and produce, science, namely computation of the calendar by observation of the stars, administration, namely annual new land surveys, and art and religion all were connected with that because of the river Nile and this rhythm which it gave to the Egyptian culture. Therefore, it's not surprising that, and it's also explicable on the basis of culture embracing sign economy, that the Egyptian numeral systems also came from this area. The number 1 in the Egyptian example was designated by 1 notch on a tally. It had the same form as that found in Stone Age bones. Now I'd like to have figure 2 if possible. So you just go the next page. Yeah. So here I've put together various possible options for number representation. And I'm now talking about the Egyptian hieroglyphs with the sign for 1, the sign for 10, the sign for 100, 1,000, 10,000, and then 100,000. And when you look at these signs, which are used to stand for those numbers, you'll see that these signs are deeply rooted in Egyptian culture, and which is determined by the river Nile. Because, as I said, the sign for 1 is a notch, for instance, on a bone or a piece of wood. The number 10, the second one, was represented by the shape of a yoke, similar to that used by Egyptian to harness oxen. So oxen, the yoke, that is 10. The design of a rolled up tape measure, the third one here, is used as in land surveillance, and it served for the figure 100. The figure for 1,000 had the form of the lotus plant, which grew in large numbers in the river Nile Valley, and thus came to symbolize abundance in the cults of Isis and Osiris, their religion. And then 10,000 was represented by the reed spadix. That's a plant which grows in shallow waters in German, reed spadix, which was even more plentiful on the Nile. And the silhouette of froth, which is the last sign which I just showed you, that was used for 100,000, since frogs appeared in Upper Egypt regularly in such proliferation, in such numbers, that they had become a plague, and the biblical plague of frogs was even proverbial in pagan classical Greece. Although the quantities of the numbers of the objects portrayed by these figures did not always increase tenfold, there was nevertheless a clear relationship between the rise of the quantities and the increase in the numerical values. So one not just for the number one, but then you have the frogs for the 100,000, which are symbolized by a frog because there are so many. I hope that's more or less clear. And if you have questions, direct questions when standing, please interrupt me so that I'm not so far away from you and we can understand what I intend to tell you. Now, the question is how the Egyptians represented nearly 1 million different numbers by means of these 6 figures. Their solution of the problem was impressively simple. There was a syntactic rule which required that the elementary sign, which is juxtaposed or concatenated, we also say in groups of up to 9. So you have up to 9 repetitions of this mark for the first 9 numbers. For the number 7, for instance, the sign for 1 was written 7 times. For 100, the 100 sign was written 4 times, 400. For a number like 2,407, they used, they represented on the papyrus a 2,000 signs, 400 signs, and 7 one signs written one after the other. That would be picture 3, really. Next one, please. Yes. No, next one. Next one, or back 3 pictures. Could we see whether that's the last one? It's the last one.
Asleep.
So if it's the last one, please go back 3 pictures. One first. Yeah, this is my example now. So if you have a number which is written as 2,407, 2,407 in our system, the Egyptians used this expression. It's rather long, but it consisted of very few different signs. So they had 2,000 signs, 400 signs, and 7 signs for 1. And this was interpreted, that's my semantic rule now, by saying when somebody uses 2 signs of the value 1,000, puts them together, the values have to be added. The same for 400, 4 times putting the 100 sign gives 400 in our sense. And the 7 also there put together, but then there's an overall addition, so that this expression, the long Egyptian expression, can be easily interpreted as showing the complex and big number 2,407. Is that clear? So I'd like to continue now and analyze with you what other possibilities there are to express the number 2,407. And I'll go through the system which the Chinese logograms used, and then the Ionian, that's Greek, type of Greek alphabetic script, and then the Indo-Arabic ciphers, and that's what we use, but there are more complex rules in the syntactic level for our numbers. Additive number codes, like the Egyptian one, are typical of most early civilizations. They were used with slight variation by the Sumerians, the Greeks, the sort of Attic figures, and the Romans. You all, I think, have learned Latin number representations. Somehow we use them still, and they are additive like those of the Egyptians, but I did not put them here especially because the Egyptians show already the principles of additive number systems. A millennium and a half after the first historically recorded appearance of these additive number systems, another early civilization developed a number code that followed a new semantic principle. So they had a new principle introduced 1,500 years after the Chinese after the Egyptians had used introduced their number representation. And this is a Chinese invention, which I'm now talking about, doing the same, namely representing the number 2,407. So the Chinese sign for 2 is this one, the Chinese sign for 1,000 is this one, and for 2,000 they don't write 1,000 and 1,000, they write 2 and 1,000. And of course, then you need another rule. It's no longer addition, it's multiplication here to get the value 2,000. Is that clear? And then you need 400, so they don't no longer put 400 signs, but they say they have a coded 4 here, put it side by side with a 100 sign, and again, you don't add, you have to multiply 4 times 100 to get 4 times 100 here, and then compose the whole number by saying it's 2 times 1,000, 4 times 100, and 7 times 1. So that's the sign for 7 in the Chinese numerograms. And the overall interpretation is now twofold. You start with multiplication in couples and in pairs, and you add the values of these complex numbers here by multiplying them. But you add them in order to get the general number. So the Chinese system gives us a smaller number expression compared with the Egyptian system. But this somehow is compensated by having not just one rule, namely addition, for the interpretation of this number expression, but 2, namely you start with multiplication and then you add addition. I hope that's clear. And this means that one could say that the Chinese had to learn more because the signs for 4, for instance, or for 7, they have to be learned. In the Egyptian system, the sign for 7 didn't have to be learned because they just put 7 times the notch for 1, and that's it. So you have some kind of payoff when you learn the number system, when you learn expressing numbers in the Chinese culture. You have to learn a little more, but the result is that the profit which you get from learning a little more is that you get smaller systems, you get less effort when you have number representation in your practical everyday life. Is that clear? My claim now is that that's something which I found out and was quite amazed about it. My claim is that in the history of mankind, in the history of the human race, we had a very small set of different number representation systems, and they differ in exactly the difference which I just showed you about the Chinese and the Egyptians. They differ in the question how many elementary signs you need, how many rules for the interpretation of complex signs built on the basis of these elementary signs you need. And so the next step, one can say, is what I put here under number 3, the so-called Ionian alphabetic script. Ionia is in Little Asia, and it's one of the Greek landscapes. And those Greeks invented a new silent system for the number representation. And in our example of 2407, they would write 2407 as beta, epsilon, and zeta. And here you see you just have 3 signs. If you want to be very pedantic, you can say 4, because this consists of 2. This little stroke here plus the beta. Now, this has to be added to this and to this. So it's a very simple rule for complex signs, but you have lots of elementary, so-called primitive signs, because you need them in order to get as high as, for instance, the Egyptians or the Chinese. The Greeks introduced their system around 500 before Christ, and their system was also connected to the Greek writing system for the Greek language, which was different from the Chinese and the Egyptians. These signs are not part of the writing system of the language, but they are part of a special system for number representations. But this is, as you all know, that's the second letter in the Greek alphabet, alpha, beta, zeta, and so on. And that's another of those letters. That's still another one. So the Greek way of doing it was also very much based on the other systems having tasks for the representation of other contents, and so there was a connection within the culture for that, which made it easier for the Greeks to use this system, to learn it and to use it. A survey of the stages of development in number representation throughout human history reveals a striking effect, and that is every advance in sign economy was accompanied by a loss in sign perspicuity. So I told you about economy just now. It becomes simpler for the representation of one complex number. Here you get 3 signs, and here, if you count them, you get something like 13 different signs which you use in order to represent the same number, namely 2407. So there seems to be something like a payoff. In order to encode the number 4, the Egyptians wrote the sign for 1 4 times in a row. This complex sign reflects in its structure the structure of the signified the number 4. The Chinese replaced it with a single elementary sign and thus transferred the generation of sign or meaning from the syntactic representation to the lexicon. So you had the Greek lexicon and not very many rules. There is nothing in the Chinese sign for 4 which reflects the quadruplicity, being 4 times or something of this number. You have to learn it, you cannot somehow see it immediately. Accordingly, the Chinese did not represent the number 400 by writing the 100th sign 4 times, but they used a complex sign which referred to the factor 4. The Greeks removed even this last piece of perspicuity. They did not construct the number in their code by forming a sum or a product. They designated it with an unanalyzable elementary alphabetic sign. Even if the elementary signs were distributed along the number arrow, as was cleverly done by the Greeks, there were still limits to this development. So maybe I should now get the first picture was born. Second, no, 2 pictures further, please. Next picture. No, next picture. Yes. Here you see the so-called number arrow. The arrow, which is used as simple for the way in which our number system, Indo-Arabic, does it. This is, and here you have the other alternatives or options for doing the same thing. Yeah, I'm going to develop that a little further, analyzing the differences between these systems. Here, by the way, that's the Ionian and Greek system, where you can see how many signs you have to learn if you don't know how to write this type of Greek language yet. The method adopted by the Greeks helped clear the way for a solution of this problem of perspicuity and effortlessness. If the signs are not tied by their form to a structural characteristic or signified, they can be used arbitrarily. They can even be so applied that they have different values in different contexts. The Sumerians were the first to come across this idea, and it was also developed independently by the Mayas, the old American culture. In the first millennium after Christ, another 1,500 years after the Greeks, the Indians constructed a complete system of number representation on the basis of this idea, which I'm telling you more about now. At the beginning of the second millennium, this system was introduced in Europe through the mediation of the Arabs. The Indo-Arabic number system, which is now our number system, has elementary signs which in isolation designates something different from what they designate in complex numeral expressions. The 1 has only the value 1 when found on the outside right of a number representation without a comma or decimal point or so. For every positional shift of this number sign 1 to the left, the value of the sign 1 is multiplied by 10. Compare the values of the expression 1, 10, 100, and 1000. So, well, you must believe me, but I'll explain what I could also have written on the blackboard. If you take a 1, it's clear that when you have a 1 and add a 0, you get 10. When you get a 1 and add 2 zeros, you get 100. When you take a 1 and take 3 zeros, you get 1000 and so on. And this shows that the value of 1, the value of the sign for 1, gets multiplied by 10 each time you put the 1 not on the right-hand side, but 1 position to the left of that. So that's a big invention and a very difficult one. It took 1,000 years to introduce that in Europe, although it was already used by the year 500 in the Indian context. It was forbidden by, for instance, the City Council of Florence in 1300 to use these signs because they said it's a system which devil has invented, and so it shouldn't be used. If the positional, we call that now the positional number code. If the positional number code established itself, nevertheless, against all those arguments, that was due firstly to its greater system economy. It did not require elementary signs in addition to those designating the numbers between or below 10 and 0 signs. So we have just 10 simple signs which you learn by heart, and then you manipulate them by computing continuum, and so on, in order to get complex signs. You don't have to learn more than 10 signs, and these are the ones which I put here. These are the primitive number signs going from 0 to 9, and the rest of all infinitely long list of possible numbers can be described by combination or concatenations of these. And the principle that makes it possible is the so-called positional value system. So we call this system a positional number representation system. I continue. The actual advantages of the positional number code lie in the following. For one, unlike any previous system, it does not require the introduction of ad hoc elementary signs for the representation of high numbers, and thus is the first number code that covers the infinite set of numbers in its entirety. This progress opened undreamed of possibilities to the sciences, astronomy especially, and of course also to administration. Think of our commercial number systems, banking. Even more important was the fact that the new method of number representation revolutionized computing. So I'm still arguing why we have gotten our system after all these beautiful other systems have been invented in a rhythm of 1,500 years. In all ancient civilizations, the principles used for the representation of a number were different from those used for doing calculations. For the calculations, the Greeks and the Romans employed an abacus, the stones made of chalk, calculi. And the Chinese had a sort of slide rule with balls on a string. It's called a suan pan. And to compute a problem set on paper, a double recoding was necessary. You had to recode the number from the paper to the computing instrument, the abacus or the sampan, then do the calculation on this instrument, and then code or recode it again to an expression on the paper. So double recoding from the paper to the computing instrument, and after the computing process from the instrument back to the paper. The Indo-Arabic code permitted calculations on paper for all essential purposes in business and trade, and thereby saved 2/3 of the coding effort. No recoding necessary. You can calculate on paper. They call it calculating on the line. Operating with numeral systems when computing is a special case of sign use, the treatment of which in semiotics is called pragmatics. So it's not about pragmatics that I'm talking, the pragmatics of number representation. And the development of the pragmatic effort in the course of history is shown in the next picture, which I'd like to read. It's the last one, I think. Oh, it's this one already. Let us recapitulate and ask us what kind of answer Leibniz could have given to the question of the King of Sweden, how to reform or whether to reform of the number representation system which they had at that time. To answer this question, we need to examine the functioning of the various components of the Indo-Arabic code. Leibniz, a philosopher, was already well aware that there were no promising fundamental alternatives to the syntactic, semantic, and pragmatic rules which he wanted to introduce instead of the system which we have. The composition of complex signs through linear concatenation of single signs is an optimal principle. The interpretation of the single signs according to their position in the complex expression is also an efficient basis for the representation of numbers of any size. Together, these syntactic and semantic rules allow, in an unsurpassed way, computing by indirect operation with the numeral systems, numeral signs. Therefore, we will certainly continue to require a code based on a positional value with my prediction. Or it was also that prediction. There is, however, room for experiment in the choice of the lexicon. We have 10 elementary numbers. You could also have only 5, or you could also have 12, or 16, or 15. This depends on the uses which you have for your system. And Leibniz was one of the philosophers who preferred a 12 system and not a 10 system. The reason was that 12 is a number which can be divided or multiplied in a simpler way than 5 or 10. Of 12 you can divide by 2, 3, 4. 10 you can only divide by 2 and 5. So this was a type of reflection which Leibniz put before he said maybe there is no need for a improvement of our system. It's good as it is already. But nevertheless, there were a number of discussions continuing after Leibniz. So the room for experiment in the choice of the lexicon is big, as I just said, and this shows in the binary system which we now have in certain contexts at least, where the computer has only 2 signs, namely the L for presence and the 0 for absence of some value. So you have only 2 positions, L, 2 signs of L and O, and with these 2 signs you reconstruct the whole number representation, although ours is a decimal one with 10 basic signs. So with appropriate programming based on the positional value, it's possible to do the same, but of course it's more complex for humans. If such a principal function does so well with machines, the binary system, is it not also ideal for humans, can be asked, and was asked. And I think to assume this would be a mistake, because humans do not operate like available machines. 2 points have to be made to account for this situation here. A neurophysiological criterion is the following. Humans are generally not capable of registering at a glance a complex sign system of more than 7 immediate constituents and processing them in short-term memory. On first reading or hearing, it is difficult for us to grasp telephone numbers which have more than 7 digits or sentences with more than 7 words. But in the binary code, a 7-digit numeral of our system has a value that lies only between 64 and 128. And for the representation of those 365 days of a year, already 9 digits are required. So the binary expression for 365 reads LOL, LOL, LOL. 9 different positions for this, where each position can only be filled by 2 alternatives. And for the representation of our number 2407, it's much more still. Then we have a pragmatic criterion. As the history of number representation has shown over many thousand years, the numbers most often used in business and trade range between 1 and 1 million. In the majority of civilizations, there were no expressions for larger numbers. The expression milliard was introduced only in the 19th century after the Franco-German War, when the payments for war disaster which France had to pay were much more than millions. That's why they invented the term milliard, which is 1,000 millions. What kind of system we need has to do with what kind of use we have for the system. If we stay in the realm of numbers between 1 and 20, like in Oceania, that's what I said at the beginning, it may be no problem to have only primitive numbers, elementary signs. If you have bigger numbers, which you want to express, you need some kind of syntax. I've talked about possible options for the syntax. And these can change. And nowadays we have, for us it's very simple to talk about hundreds of thousands, or let's say even millions of whatever money it is, euros or dollars. But the system for the description must be such that these complex signs can be easily read and don't become too complex for us to memorize them upon reading. Leibniz had already experimented with positional codes in which shifting a figure one position to the left did not lead to increase in its value by the factor 10 as in the decimal system, but by the factors 8, 12 or 16, I said that already. Finally, he proposed the King of Sweden, a positional system that was based on the factor 12. It was called a duodecimal code, in which, although two new basic signs had to be learned, 11 and 12, division and multiplication are more easily carried out than decimal system. From a political point of view, it must be said, however, that the difference between such systems, the binary and the duodecimal and decimal system, is so slight that it would never justify the cost of replacing the universally established system with a new number system. Everything indicates that the historical development of systems for the number representation, which has been progressing steadily with 1,500 years since the early civilizations, reached its final stage with the introduction of the decimal positional code. This can be concluded from the course of the central figure here. I have put the various dimensions of judgment about the value of one of those sign systems here. I start with the lexical effort. So in the beginning, you only have 5 or 10 elementary signs. And when you continue in time, this was 3,500 years before Christ. When you go in our direction of time, and you are 500 before Christ, you have a system which doesn't have 5 or 10 elementary signs, but 30, because it's based on the alphabet. That's why this line goes in this way. There's a hill here. But the Greek system did not survive. It survived for some small purposes, like counting, or let's say, in counting it is used, also the designation of sides, paper in books, for instance. There they still use the alphabetic one, but not in other cases. Then the question is, what is the development of the other dimensions? The lexical effort had this development. The syntactic effort, this is the line which is broken in this way here. It started with a very simple additional system here, and then addition plus multiplication, that was the Chinese solution, and then multiplication in the same way, but with another semantic rule was used by the Arab and Indian system. And so that's why the syntactic effort has this small hill development. And the similar can be said about the semantic effort. where the problem, the main introduction was the positional value system. And then I have a dimension of performance effort. That means how many signs do you have to put on paper in order to designate a complex number. And evidently, when you have a more complex semantic rule, you have less complex performance. And that you have it, that I put here, and that's the line, which comes in waves like this one. The pragmatic effort was the effort which I talked about when we had the question of complexity, but also the question of which types of numbers you want to deal with all the time, small types or big types or medium types. And that's what is here. So after the invention of the position system, these lines all go down. The so-called number of elementary signs gets less, and at the same time the number of rules becomes at least less complicated. And so this is a schema which shows you the development of number representations in the last 5,000 years. And the question is still, it's up to you. I have the following question. What do you think? How come that we have this very regular development? Every 1,500 years you get a different system. That's question number one. Question number two is, if you were like this yourself, what kind of number system would you prefer? Which of them, or do you have another one? Thank you very much.
So questions maybe?
Yes.
Questions. Can I ask you maybe it's a very simple question, please? I'm sorry. You said that probably, you think that probably our first impression would be that this theme is far away from what we are doing. But then you said that it's not true, it might be interconnected somehow. And my simple question is about this Arabic system. Do you think that it still exists, you still use it, because it was so clear, because of it, like, you know, because of its design? Because the design is so clear and transparent and easy, so we still use it. But very meaningful, and there are multiple meanings into it.
I think the situation is a little more complex. This is shown by history. It really took 1,000 years for the Europeans to accept this system against the Roman system, or also against the Greek system. And the question is, why did it take so long? And I think the main problem which they had was a genuinely semiotic problem. Namely, how, and we have wonderful tractates, we have wonderful, let's say, systematic thinking about that in the 15th and 16th century. They say, more or less, they ask the question, how can something which is nothing, namely the cipher 0, when you add it to something, make that something become much more? How absurd is that? That's how they formulated it. And by formulating that in that absurd way, they were, of course, driven off of trying to use the system. And this is just one of the arguments against it. The other one, type called the pragmatic problem. The pragmatic problem was the bankers in Florence at that time. They said, this is a system that invites cheating, because you write a 0, it means nothing. But then you write a 0 to the left of that 0, and write a 1 to the right-hand side. The expression as a whole is 1. But when you turn them around, you get 10. So how 10 versus 1 versus 0 can be changed so easily. That's devil's work. The devil makes us use this system because he wants us to cheat each other more. So, I mean, we have this type of argumentation. And I think especially it was a great semiotic invention to introduce a sign, like the sign for zero. This is also shown in, let's say, the etymologies of many cultures. The Greek and the Arabic term for zero is cipher. Cipher or chiffre, or process of chiffre. So chiffre has another meaning, which is not number sign, but it's something like a very complex, intransparable sign. Chiffre is something that you don't understand, something which you cannot analyze, and which you cannot explain its meaning. So we have that, that's our tradition. And so I would say it's not because, or not primarily because of this effort problem, but it's also primarily because other aspects that we use them now. Now that we use these numbers, of course it would be, take the problem of effort again, it would be too much of an effort to introduce something which is only slightly better. That was Leibniz. He said, stay with your system, it's okay. Maybe the duodecimal system or the 16th system is a little bit more efficient, but this does not allow us to change because the change is too expensive.
But you just said it was the invention of the introduction of the positional system, so the rejection of it by the Venetian or Florentine bankers was based on the suspicion that it could be used for cheating. But I think it's also much more sensible to mistakes. So the other systems, the multiplicative or the additional numbers, it's much more stable system. If you use it only in let's say for small numbers, maybe from 0 to 100. But then when it grows, then probably you have to switch to the positional system at the same time. It is also it's more open to mistakes. So you have to invent a certain discipline to handle numbers.
Yes.
Therefore, probably it goes hand in hand also with the organizational restructuring of the entire banking sector. And it's very interesting, for example, in Japan, so they still use both systems, the positional and the, what is called the additive, no? The multiplicative number code, yeah. For example, in the menus, if you go to a restaurant, in the menus, so in traditional Japanese restaurants, you use the multiple multiplicative number systems because it's small numbers. So you pay maybe 100 yen or maybe 1,500 yen. So it's very easy to handle these numbers. This is interesting because this follows your argument that you have small numbers. Also, the other systems work quite well, or even better, because they do not lend themselves so much to mistakes.
Yeah. I totally agree. Yeah. And you can see that easily when you have old code, old texts. Very often old texts are not written from left to right, sometimes from right to left, sometimes from above to below. Very seldom from below to above. But when you have early codes, you have numbers, let's say, collected as number signs, which to us seems very untidy. They are not clearly in a line from left to right, not clearly in a line from up below. But it's not necessary because when you have permutation, you don't have a different mean. So it seems some progress, but of course, it becomes progress only with more differentiation and more discipline. I agree.
I have a question. Yes. let's say in a digital world we use only two numbers. Does it mean that in future the typical traditional system will disappear or not?
That's what people ask a lot of time, even let's say 50 years ago. In the last 50 years, the question was, does the human brain work like a computer? Yes or no? And one of the questions was, if, like a computer, should we all change into a binary system? And the answer I tried to give already is, binary system is okay, it's wonderful, it's very cheap, also very lack of effort for machines, but not for humans. Because humans have this memory problem, which machines don't. So one can say that if one makes this hypothesis that the neurophysiological structure of the human brain is very near to the neurophysiological structure or to its equivalent in computers, I think that's a big mistake. And we had conferences about that in the 1970s in Berlin, where people were fiercely against each other. We had two parties. One was, yeah, it's quite clear everything's going to be computerized. Humans should also be computerized, that they can communicate with the machines on that level. And the other said, no, it's the contrary. Machines are humanized.
I would like to add to my example, Japanese example, because it's more complicated, more complex. Because on the menu, often you have this multiplicative number code. But then, when it comes that you have to pay on the receipt, it's always the positional code. Because when you have to make the calculus, then you need necessarily the positional code. So, but when you order, so you order, let's say, main dish, starter, and so on. Of course, it's only single numbers. So this is why you can work with the multiplicative numbers code. It's very easy. But when then you change, when it comes to the calculus, if you want to add things, then they change to positional number code. So because it's more pragmatic, and I think it's very convincing that it comes to this. In the end, the pragmatic level, and there, of course, some of the syntactical system works much better than the semantic system. In pragmatics.
I agree. There is another slight pragmatic factor there. When I first saw menus, they didn't write, let's say, soup, €6.25. They only write 6. They don't, for a steak, they look like 20 euros, 78 euros. They write 29. And I found that that was an aggression against my rights as a customer.
It is almost a regression to the multiplicatory number code, because then the 20 stands almost like the Japanese when they read the 20. So it's a regression in the progression of the system and the number system.
You could say it's a lexicalization of the
Lexicalization, yes.
Of the product.
Exactly.
Yes.
I think why the Arabian system representation of a number use a lot of people nowadays, but Arabian language is not popular. How you see?
I didn't quite understand. What is not popular?
It's not popular Arabian
Arabic.
language. Yes, Arabic, the language.
Well, I mean, what language one has seems to be.
We still use the numbers, right? The system, the Arabic system in numbers. It's still like alive, right? But not the language, not the Arabic language.
Yeah. Or what is it?
That's
That's a question, and I guess it's
it's
a very interesting question. I think it's very near to my answer, very near to what we just discussed. Once you have a system, deleting it and using another one is an enormous effort. That's why Normally, cultures develop in such a way that they modify what they have given. And in fact, that was similar also with the Arabic system. The Arabic system was not written from the left to the right at the beginning. It was written from the right to the left, and sometimes also from above to below. The Chinese from above to below, Japanese also. Now, these are little changes, but they are necessary to adapt these systems to the context of those people who use them. And so I would say it's primarily a political problem, how strong is the culture, so that other cultures use their system even if it's more complex. It's the same, for instance, for a mathematician, why do we use the English spelling? Because it's so erratic, it's not very well ordered and very complex. Evidently, using a form, the English spelling, would be such a big effort that people don't want to take. So it's a political problem, and the costs will have to be somehow compared.
And there's another thing to it. For example, the Koreans, they changed their language. So they simplified Japanese, the Chinese characters into what we now know as the Korean characters. And that was a part of the culture. Because if you're not anymore, so the modern Koreans who are not able to read the old Korean, the Chinese characters, they are not able to read the old texts of their own culture. So this is probably also a question why the English writing is still, they stay to it, because otherwise if they would simplify it, they would forget about how to read their old text, Shakespeare for example, or only those scholars would be able to read it, but let's say every common man would not be able anymore to read it. It's a big problem in Korean culture. This is why also the Japanese stay to their system, although it's a difficult, very complex system.
I think the question is much more difficult and deeper than it seems. We all, I would say, the majority of Western cultures, especially Western European cultures, as such, don't believe in Christianity anymore. The majority don't believe. But if you ask them which kind of schools do you want to put your children, yes, they should learn all that so that they know why they don't believe, for instance. If you take the results of schools which don't have any religious learning anymore, that's not a progress for many people because there is a lack of communication, lack of possibility to understand that one's own culture has developed. And maybe the present state is better or worse, but the fact that one can ask this question is lost. So I think it's a very important project.
Now we know.
Yes. Yes, in Russian, Irina will ask in Russian, I will translate it to you.
Если я правильно поняла, то переход на позиционную систему исчисления хронологически совпал с научно-технической революцией и вообще с развитием естественных и точных наук. Вот есть ли действительно какая-то взаимосвязь между этим?
Irina is asking, yes, to make it clear. Is it possible that this transition, like using of positional system, yes, positional system, they started using it, happened at the same time as the revolution in science, yes, humanities and natural science, yes, the growth of manufacturing. Do you think there is it's just a coincidence or it's really interconnected? These historical facts, they are interconnected.
I think they are heavily interconnected, and I try to do that a little bit by what I said about the river Nile. But of course, the question is, what happened when the Europeans slowly started to use the Indo-Arabic system, it's quite clear that at that time the Indo-Arabic, the Arabic Muslim culture was far advanced compared with what was left of the antiquity in the Western European countries. So there is some reason why the Islamic system was gaining ground at that time. It was only later that these discussions became important. But around the years between 800 and 1100, it's no question that we should use the Arabic way of number representation.
Это было связано с тем, что это просто удобная система исчисления, или это как-то легло на структуру мышления, подходило под структуру мышления европейцев?
Did it happen due to the fact that it was just easier to use this system, or more maybe it was connected again with the mentality of the people living in that?
I think it's very much important.
Structure of cognitive process.
Well, my opinion and impression from reading books about what should be done at that time is that it's a more political problem than a problem concerning effort and concerning usability. When the political stress is so strong that everybody else uses a more difficult system, you will also use a more difficult system in order to be able to communicate. That's, I think, the reason why, even if, for instance, English is not a language that is more efficient on many levels. It's efficient on some very important levels, yes, but it's a political question whether we speak English or Spanish or Russian or Japanese.
Some more questions?
Thank you.
I have. It's maybe. It's not a joke. I thought about it when you were giving the example with broken numbers. You said that, like about euros 26, a comma, for example 98, like prices. Why do you think Europeans and Russians we use commas in broken numbers, and in the United States they use dots? How can you explain that? Maybe did you think about it?
Well, I think when you go back in time, you have more than dots convention, and so it's just two options which you have. If you take the possible reservoir of these so-called helping signs for letter systems. I think it also has to do with prestige. For instance, in psychology, even nowadays, also Germans use the point when they use American type psychological rating systems for experiments. So,
Just conventional.
Well, the interesting thing is we talk about languages not only as codes, not only as systems for communication, but also as systems for identification of communication partners. And that's the important thing. Whether you use the American transliteration or the British one concerning present-day English is, I think, some kind of declaration. In the early 70s, when I started the journal Zeitschrift für Semiotik in German, we had to decide whether we take the North American or British system for the English subtitles. At that time, I thought, well, the number of people using American type English in the world is bigger than the number of people using British type English. So let's have the English summaries in this journal in American type English. I still use American type English now, but I think it may have been a mistake because all Europeans I know tell me, why do you use American translation? English is a European language. We should all use the English transliteration. So you have these, let's say, language sociological aspects which are very important, and they interfere with those questions about effort or effortlessness. also transparency.
Thank you very much. Well, thank you very much. So it was just the first lecture by Professor Posner. Thank you very much. We'll see you tomorrow. We hope that everything will be fine. We're not going to touch anything. We just leave everything like that. We're not going to give it back. So tomorrow at 10:30 we'll start. And the theme, maybe you could represent the theme of the lecture tomorrow, just the title.
Yeah. Well, tomorrow it will be about perception. Perception is a very interesting and very controversial type of science process, I would say. There are people who say perception is a science process. Science process starts when you have started to perceive. And so I'd like to discuss this problem. And it has to do with, as Umberto Eco would say, what is it? The first entrance into semiotics. What we would like to say is a discipline, a subdiscipline of semiotics, or there is something else. So I'm discussing that, but I'll be very down to earth, like what a competition should be, always related to science and scientific complexity. So I'm going to start by discussing the definition of what is picture, and then I'll continue. So it will be about, let's say, old-fashioned visual science system, but it will be very easy to be connected with, any type.
So we are expecting tomorrow. I guess there will be some new part of the videos which will be present here tomorrow. Thank you very much. Спасибо всем большое.